Today, we're going to analyze the gain of this common source MOSFET amplifier. So let's get started by first finding the DC bias point of this circuit. So in the DC regime of this circuit, we can treat these three capacitors, 1, 2, 3, as open circuits. So let's just go ahead and erase them to show the disconnects in the circuit. So this first capacitor, we erase it. The second one, we get rid of it, and so too with this third one. So now we see that we really only have to worry about this central, block of the circuit here. It's already become so much simpler. So it's also important to note that no current really is going to flow into the MOSFET here through the gate. This is the gate node. That's just the definition of the gate. So we can also sort of treat this as an open circuit. And if we do that, we see we literally just have the most simple voltage divider. Literally voltage here and two resistors, boom, boom, that's it. And that's all we need to do in order to find the voltage at the gate here. So this voltage at the gate can be found simply through, standard voltage divider equation. So the voltage divider equation says that the voltage at the gate is going to equal this voltage, 100 kiloohms, divided by 100 kiloohms plus the resistance here, which is 180 kiloohms. And then that's going to be multiplied by the total voltage, which is 12 volts at the top here. Let me add in the units here just so we're consistent. That's going to be multiplied by 12 volts. And if we go ahead and just solve for voltage at the gate, then VG, we find that that is equal to 4.2857 volts. So this is the voltage at the gate node right there, and because this is a short, it's an open and a short at the same time, which is sort of strange. But because this gate is, a short to this node here, this is literally this is the voltage of interest, right? It's literally the voltage right on this part of the circuit right there. And through that, just knowing the voltage at this gate, we can then go ahead and find the current through this MOSFET, ID, the drain current, the current through the MOSFET. If we assume that this MOSFET is operating in a saturation regime, then we know that the current through the MOSFET is given by the following equation, which is ID equals 1/2 K times VG minus VS minus VT all squared. So here, VG is the voltage at the gate, which we just found. VS is equal to the voltage at the source, which is right there. And then VT is the threshold voltage, which is already given. It's 2 volts. So, and K is also given, which is just some multiplicative, coefficient. It's 2 milliamps per volt squared, just based on the properties of the transistor given in this problem. So this is an equation which is very important. This is the saturation equation. And then we also can just apply Ohm's law to know that the current flowing through this MOSFET also has to, this is just the current flowing through this resistor here. It also just has to be the current that satisfies Ohm's law here. So Ohm's law says that the current flowing through this resistor is going to be the voltage difference across this resistor, Vs minus ground, which is Vs minus 0, divided by the total resistance, which is 1 kiloohm or 1,000 ohms. So here, let's just go ahead and, in this equation in the bottom here, let's just plug in what we know. Well, we know that 1/2 times, what's K? K is 2 milliamps per volt squared. Let's convert milliamps to amps by multiplying by 10 to the negative third. Then we already found VG, which is about 4.29. Then we don't know VS yet, but we do know VT, which is 2 volts. So we can plug in 2. This is all squared. And then we don't know VS on this side, but we know it's divided by 1,000. And now at the very bottom of this chalkboard here, you see that we literally just have a one-line equation with one unknown. So if we go ahead and subtract Vs divided by 1,000 from both sides of the equation, we then can, convert this into 0, because if we subtracted Vs divided by 1,000 from both sides, then the right-hand side just equals 0. And then here we see that we just have this quadratic function of Vs, where Vs is the independent variable. So we can literally just call this f of Vs. This is just some quadratic function of Vs, and we want to find where this function equals 0. So if we were to plot this function as a function of Vs, it would literally look like some, there's a squared here, there's a linear term here. It would literally look like some quadratic function in terms of Vs. And we're interested to know where this function is 0, where its roots are. So if you were to go ahead on Desmos and plot this function and find its roots using Desmos, don't use the quadratic formula, that's just too tedious. You'd find that one root is at approximately 1.19 volts, that's this root, and then this root is at 4.38 volts approximately. So you're probably thinking, well, how do we know which it is? That will determine what Vs is at this source node. So how do we know what it is? Well, if it were this, 4.38 volts, let's see what that would imply. Well, if it were 4.38 volts, then let's see if this MOSFET would still be able to be in the saturation regime, which was, of course, our original assumption when we used the saturation equation. In order to be in the saturation regime, we know that, Vg minus Vs has to be greater than Vt. This is a requirement in order to be in the saturation regime. We know that Vg is 4.28. Then if we allowed Vs to be 4.38, well, that's not looking good because Vt is 2 volts. So this would be saying that, some negative number is greater than -2. That's obviously, or is greater than +2, excuse me. Some negative number is clearly not greater than +2. That's a contradiction. So this root here, not possible, not a valid answer for the voltage at the source. Therefore, this 1.19 volts, this is an approximation. The true value is like 1.19332, blah, blah, blah. But this is the only valid voltage at the source node. So if we go ahead and run with this as our number, we can then go ahead and calculate ID, which is the total current, because that's obvious. It's just, it's just Ohm's law. We know that, we already said that ID equals Vs minus 0 divided by 1,000. We literally already wrote that equation here. We now know Vs, so that literally means that ID is just 1.19 milliamps. That's the total current through this through this MOSFET. And then using this current, we also know that this would be ID right there, that the ID would also have to be the current in this upper drain branch because no current can split off through the gate here. This is, virtual open, it's virtual open and virtual short, which is kind of strange, but this is virtual open. And so therefore ID has to also be in this branch. So that means we can then solve for VD, the voltage at the drain node, again using Ohm's law. We know that the total current flowing through there, ID, has to equal the voltage difference across this resistor, which is 12 minus VD divided by the total resistance, which is 4.7 kiloohms. And of course, we just found ID to be 1.19 milliamps. And therefore, we literally can just solve for VD in this simple, two-step equation. And if we were to do that, we would find that VD equals 6.39 volts. So we've literally just solved for all the possible, DC bias conditions in this circuit. If we ignore the AC components, only DC. We've just solved for the DC bias conditions. And then one more thing before we move on, let's just once more verify that this, with these new values we have, that this MOSFET is indeed still in the active mode. We verified that this condition, this VG minus VS is greater than VT. We verified that that's true, but let's verify the other condition for being in the saturation / active mode. So the other condition for being in the active mode states that VDS has to be greater than VGS minus VT. So what do these, this is a textbook, you'll find this definition in textbooks, but what do these like double subscripts mean? Well, this just means VD minus VS. VDS just means the voltage difference between the drain and the source. Same thing for VGS, this just means VG minus VS, and then we tack on this VT here. We can then cancel VS from both sides, and it's clear now that the last condition for ensuring we're in the saturation mode is VD has to be greater than VG minus VT. So is this condition satisfied? Well, VD, we just solved for that, that's 6.39. Is that greater than VG minus VT? Well, VG is 4.28 and VT is 2 volts by definition. So this is clearly true because this is a number around 2 and 6 is clearly greater than 2. So yes, we are definitely in the saturation regime and we were correct in using the saturation equation. Perfect. Now let's move on to the AC analysis of this circuit, which is going to be a little bit more in-depth. So the AC analysis of this circuit is going to entail re-looking at the same circuit in a slightly different way. So before we go ahead and do that, we first need to calculate the transconductance of this MOSFET here. So the transconductance is going to equal, it's going to be the partial derivative of the MOSFET current with respect to the voltage difference between the gate and the source. So this is what we're going to need to find. If we take a look at this first equation up here, this saturation equation, we can actually just differentiate this equation with respect to the difference between the gate and the source. So we want to differentiate that equation. We already know from that equation that ID is equal to 1/2 K times VG minus VS minus VT squared. This is the saturation equation I wrote on the board above. So if I take this partial derivative of ID with respect to VGS, where VGS is just, it's literally with respect to the difference, which is VG minus VS. We're literally saying that this is one variable and differentiating with respect to this variable. Well, we can then use the power rule, bring down the 2. That's going to cancel with the 1/2. And we're literally just going to be left with this. So we've gotten rid of this quadratic term, and we literally are just left with, this was our independent variable, when we're differentiating this difference. And we're literally just left with this. So this is how we're going to calculate the transconductance, which is defined to be this partial derivative. But it's also then important to evaluate this at the DC bias point. So, the transconductance, we're then going to evaluate this at the DC bias point we just found, which is going to be V capital G minus V capital S minus VT. And these capitals are important because they represent, the DC components, the components of the circuit that don't change with respect to time. They're just sort of constants, direct currents, no time variation. So this right here, this K times VG minus VS minus VT, this is how we find the transconductance. That's how we find this. And this is all just defined to be GM. We give it a special name, GM. So how can we calculate this? Well, I think we have everything we need. We said K was 2 times 10 to the negative 3. We said VG was around 4.28 or something like that. We said VS was around 1.19. And we said VT was 2 volts. So if we just go ahead and do that, we find that the transconductance GM is going to be equal to 0.002. It's going to be 0.002185. This is going to be, this is going to be amperes per volt. So it's a conductance, so it's the opposite of volts per amp. It's amps per volt. So that is an important parameter which you're then going to incorporate into the AC version of the circuit. So whereas before we sort of looked at the DC version of the circuit where the capacitors were open circuits, we now want to look at the AC version of this circuit. And because, you know, the capacitors are, you know, generally thought of as open or as short circuits in the AC regimes, we're going to short out the capacitors. So these capacitors become short circuits like that. This becomes a short circuit, so it literally just, you know, replace it with a wire, not with an open switch. Now we replace these with wires. And we also, just based on sort of things that are beyond the scope of this video, we also still treat that as an open circuit. So that sort of, this bridge here is now no longer, you know, a virtual short. It's just a completely open circuit at the gate node there. So this is VG. And then the last thing I want to do is I want to also get rid of the DC elements of the circuit. So these direct current 12 volt, you know, sources up here, I don't care about those in the AC regime of this circuit. In the AC version of this circuit, those are both ground. So replace those DC sources with grounds. And I lied, there is one extra detail. I want to incorporate the transconductance. So this MOSFET here, we can replace with a current source using the transconductance. So current sources get this diamond shape. That's actually not a very good diamond. We're gonna redraw that diamond in a little bit of a better way so you can really see it. We replace that with a diamond, and this diamond is a current source which is controlled by VGS. So it's going to be GM, the current flowing through this diamond is going to be GM times VGS. And of course, this is VS, and this is VD. This signal, it's important in the AC regime to use lowercase letters, so I'm just going to change these to lowercase letters. And the same thing for V out. I'm just going to change this to lowercase letters so we're all consistent and we're not still thinking we're in the DC bias regime. So now, this is the circuit we now have to analyze if we want to find the ratio or the gain between V out and V signal. So how do we go about doing that? Well, let's just go ahead and maybe redraw the circuit in a way that makes our lives a little bit simpler. So if you notice, we have some, circuit here which is all natural, but then it has these two branches, one resistor to ground and another resistor to ground. So is there a way that we could just, make that a little bit more palatable when we look at it? Well, let's redraw it here where this is V signal. We have this 100 ohm resistor, and then let's just put both of these resistors to ground right here. We got this 100 kilo ohm resistor to ground, and then this 180 kilo ohm resistor to ground, and this node is of course still VG. So this is completely palatable, right? We've literally just flipped this resistor down to make it a little bit more, understandable. And then also, let's just notice, because this is a short circuit, no current flowing here will always flow through here because there's literally no resistance. It's perfect. Current will flow where there is zero resistance always. And no current will choose to flow through this path, which contains 1,000 ohms of resistance. So we've literally shorted this this resistor out of the picture, because by providing this zero resistance path here, we've literally gotten rid of this resistor. You know, no current will ever flow through it because it will always take the easier route. So it literally doesn't matter. It's a dead branch of the circuit. So we can literally get rid of that. And then let's also now, this literally has just turned this, VS into ground. It literally just grounded the source. That's where we get the name common source amplifier from. Common source just means that the source is grounded. That was a little foreshadowing. And now that we've done that, let's also just flip this top resistor down right here. And it literally becomes almost the simplest circuit in the world, because we have this diamond here, which goes to ground, right? This diamond leads to ground. And it literally just comes from these two resistors, which also just come from ground. Literally 100 kilo ohms and 4.7 kilo ohms. So if you take a look at now this simple circuit, this is so simple to understand. It's literally just two simple little, resistor circuits. And then we also just need to remember that this current source here is GM times VGS. And then the last thing I also then want to note is, let's combine these parallel resistors into single resistors. That makes it even easier. We can literally just get rid of these double parallel resistors and turn it into one resistor that's, equal to the equivalent to both of the resistors in parallel. So this one resistor will be equal to a 100 kilo ohm resistor in parallel with a 180 kilo ohm resistor. We just have to remember that. And then this, get rid of this one. This one will just equal a 100 kilo ohm resistor in parallel with a 4.7 kilo ohm resistor. Boom. Wow. Is that simple or what? And then finally, let's just go ahead and use our simple, Kirchhoff's, current laws to solve this circuit once and for all. And you don't even need that. You just need Ohm's law. So using, first of all, let's use the voltage divider rule here. We know that VG is going to equal 100K in parallel with 180K, all divided by that parallelism again, 80K, plus this resistance at the top, 100 ohms, times the total voltage, which is V sig, perfect. And then let's just literally use Ohm's law. We know the current flowing through this branch is GM VGS. And that, of course, then has to equal, the voltage difference between this resistor. And I also forgot to point out that this node right here, this whole top node is V out, of course. That just comes along, V out just comes along for the ride. It is just, naturally there because it is the voltage across this 100 kilo ohm resistor. And it is also the voltage across this 4.7 kilo ohm resistor. So literally this current here has to equal the voltage difference here divided by this resistance. So let's be careful about the signs though. The current is flowing down, meaning the current is flowing this way, meaning the current is flowing up. So when you use Ohm's law, we have to be careful to take this minus this, because you always go from this side of the arrow to the pointy side of the arrow. So it's literally going to be this voltage, 0, minus the top voltage, V out divided by this total, which is 100K in parallel with 4.7K. This little double line symbol means parallelism, means resistors in parallel. Then let's make a few more simplifications. VGS, well, what is that? The definition of that is VG minus VS. And what is VS? Well, VS is 0. It's ground. So it's 0. Let's zero that out. It's literally 0. Doesn't matter at all. We only care about VG. Okay, so finally, now let's go ahead and we can also get rid of this 0 here because it's just 0. Then let's go ahead and divide this equation by GM on both sides. So we get rid of the GM on that side, and we're just left with VG. And then the GM just comes down here into the denominator. So we literally just put a GM into the denominator. And then we literally just have one expression for VG and another expression for VG. So let's equate these two VG expressions and just say that, you know, this equals this. And if you go ahead and rearrange that and write everything out, you know, you're going to have to divide both sides by V sig to find the, you know, the ratio we're interested in. You're going to have to multiply by this denominator. If you just go ahead and write everything out, you're going to find at the end of the day that V out over V sig is going to equal negative GM times 100K in parallel with 4.7K times 100K in parallel with 180K, all divided by 100K in parallel with 180K plus 100. This is the final gain of interest. This is the ratio we were after from the very beginning, and we literally have all the parts we need. When you want to calculate these parallel, you know, these parallel resistors, you just want to remember that, you know, for example, 100K in parallel with 180K is equal to 100K times 180K divided by 100K plus 180K. That's literally what the parallel operation does. It's if you have A in parallel with B, it literally is A times B over A plus B. So that's how you go ahead and calculate all those parallel expressions. And if you go ahead and calculate those parallel expressions, remembering to put in a 1,000 or a times 1,000 wherever you see a K, don't forget about that kiloohm, don't forget about those units. And then you plug in our value for GM, which we already calculated to be like 0.002185, blah, blah, blah. You'll find that the final gain, V out over V sig, V signal, is equal to negative 9.79. And that is a unitless quantity because it's a voltage divided by a voltage. And this is a pretty good gain. You know, if you take a look at what something like this gain actually means in the context of engineering, it means that if you plug in a very small signal over here, I'm actually going to erase this to just show it. It means if you plug in a very small signal for V signal, you know, something like this. Let me just draw this. You're going to end up getting an output signal for V out, which is going to be 10 times or, you know, negative 9.79 times as large as the original signal. And it's also going to be inverted from this minus sign. So you're literally going to have like a signal 10 times as large